A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians! Welcome back to another video. We've been talking competitive math problems yet again today, and in a normal case with those, I'm going to present to you the first way I have solved this problem in the first place. But this time I'm going to show you my second attempt on this problem because it's way more ingenious, if I may say so myself. There was a real stroke of genius from my side there, and you can find my original attempt over on Flammable Maths 2 as well as another outtake video. So make sure to go over to Flammable Maths 2, watch it and subscribe to the channel if you haven't done so already. And now we are going to dive right in. We'll be talking Putnam 2018 problem A1 today. Find all the ordered pairs AB where A and B are element of the positive and negative integers with 1 over A plus 1 over B being equal to 3 over 2018. And this is not congruent, this is identically equal for all of those who don't know yet. And we're going to dive right in. So at first, I would like to bring 2018 to one side and all the other number bunch to the other side. Why am I doing this? Well, because the number 3 can't really be factored. It's a prime number already. We would like to factor 2018 here, because then we are going to have 2018, for example, being equal to some mapping with respect to A times some mapping with respect to B, and those prime factors we can decompose and find combinations of A and B here. This is the plan behind all of this, and we're going to start by adding those two together. So expanding 1 over A by B over B and 1 over B by A over A. You might notice that our problem is completely symmetric. I will come back to this in a second. Meaning we are going to get A plus B over AB being equal to 3 over 2018 for now. And now obviously we don't want this fraction to be equal to 0, meaning we don't want A plus B to be equal to 0, so that's a given because this wouldn't satisfy this equation right here. So meaning we can divide both sides by this factor, and then we can multiply both sides by 2018, that's also not equal to 0, leaving us with 2018 being now equal to 3AB over A plus B. And I said before that our problem is completely symmetric in A and B. So each and every pair AB is the same as each and every pair BA in some way, so we can interchange A and B freely because addition is commutative, obviously. And this gets rid of a bunch of extra solutions that we don't want to have, and also it makes my trick possible that I'm going to present to you in a minute. Pretty nice trick. So what was my initial thought when I saw this right here? So what I told you a second ago is that I would like to decompose what we have here into some kind, I don't know, let's say x of A times x of B, okay? Because then 2018 can be decomposed into its prime factors. You really should know how to decompose the year you are in, for example 2018 or 2020, into prime factors if you are dealing with a competitive math problem. So 2018 overall is nothing but, okay, it's divisible by 2 obviously, so it's 2 times, and 2 times 1009, and 1009 is indeed prime. You can use the square root test, for example. So meaning, since we are in a unique factorization domain, for example, we can say, for example, that xa is equal to 2 and xb is equal to 2009, for example, and then we can find extra solutions, or xa is equal to 1 and xb is equal to the multiplication of those two prime factors, and maybe that's a set of solutions. That was my initial thought here when I approached this problem. Meaning, I would like to decompose this into the multiplication of two things, one with respect to A and one with respect to B. But here comes a real problem in. We have an additive denominator, which makes matters extremely worse. We can't really deal with this nicely. This is why I was trying some kind of polynomial division on my side here. Meaning, for example, our b is nothing but x, and then try to do polynomial division here. And this is what I came up with, which comes in quite naturally actually. So we are going to take a look at this fraction, 3ab over a plus b. What I would like to do is I would like to cancel out the denominator in some way. Okay, this was my thought here. Meaning what I would need to get up here in the numerator is some factor of a plus b. How could I get this? Well, I would need to add something to this numerator up here and subtract it yet again, adding a nice little 0 here. So adding 0 really doesn't change anything. If you add no apples to your 3000 apples, you still have 3000 apples, okay? But what could this 0 possibly be? I would need to factor out a plus b in some way. Look at this. So after trying around, it's all about try and error here, to be honest. 3ab plus 3a squared. I need the factor of 3 here because I would like to factor it out together with bunch of other stuff such that I can get a plus b into here. And you see 3a is a common factor of those, and if I factor 3a out we get b plus a, which is exactly what I want. And obviously we need to subtract 3a squared yet again because we want to add 0. 3a squared over a plus b. Meaning this is going to give us, okay, factoring out a plus b, 3a over here, I'm terribly sorry, this is going to give us 3a times a plus b minus 3a squared over a plus b. And now we can just use the additive probability of the numerator to get 3a minus 3a squared over a plus b. That wasn't any good yet, but look at this. We have a common factor of a here. Let us factor this out, and then you might notice where I'm going here. It's actually pretty ingenious, to be honest. We're going to get a times 3 minus 3a over a plus b. Okay, this was my polynomial division that I did here. And one thing you might notice here is that only a b in this numerator is missing to get ourselves 2018. If we were to get a b into here, okay, bunch of b's, then we would get 2018 and our polynomial division would be kind of done, because this right here is with respect to a, for example, only with respect to a and not with respect to b anymore. Exactly what I wanted. This is xa. And also don't forget, our problem is completely symmetric in a and b, meaning what we did here for a can also be done using b. So what we would need to add is 3b squared minus 3b squared, and then we would get 3b minus 3b squared over a plus b. So let us write it out. So this thing is actually also equal to b times 3 minus 3b over a plus b. Okay, problem is symmetric. This is nice and Gucci, but how does this help? Well, cool thing is, multiplication is commutative, and this is where it struck me like lightning. That was extremely amazing. If we were to multiply those two together, then we would have a times this factor times b times this factor, but we can interchange a and b because multiplication is commutative. Tracking the b into here would give us 3b minus 3ab over a plus b, and this is exactly 2018. And if we were to multiply the a into here, we would get 3a minus 3ab over a plus b, which is 2018 yet again. Meaning we can decompose this into the multiplication of two factors exclusive to a and b. Okay, and this is pretty cool. So let us multiply both of those together. Don't forget, each and every one of those was equal to 2018 originally, meaning we are going to get 2018 squared is thus equal to, and now we are going to write this out. I'm going to bring the factor of b into here, leaving us with 3 minus 3ab, 3b, sorry, we are going to track the b into everything, over a plus b, and then I'm going to track the a into this factor, times 3a minus 3ab over a plus b. And don't forget, this right here is equal to 2018, and this right here is equal to 2018. I am so excited because this is so cool. This kind of polynomial division turned out so nicely. It just turned this thing into two factors that we can make use of when decomposing it into a multiplication of prime factors, so prime product. So this is nothing but 3a, okay, multiplication is commutative, I'm going to use a before b just because, minus 2018 times 3b minus 2018. Ah, this is so good. This is so good. And now don't forget how we can decompose 2018. 2018 is thus nothing but 2 squared times 1009 squared, being equal to 3a minus 2018, and then times 3b minus 2018. And thus, the deal is basically settled. All we need to do now is compute each and every part in here. What computation means, I'm going to explain in a second. And then we just need to see if it's divisible by 3. Why divisible by 3? We will see in a second. Let me explain first. So here we have the product of things, and here we have a product of things. Since we are in a unique factorization domain in normal case, so meaning if this is decomposed into a product of prime factors, then this multiplication must also be without loss of generality, be decomposable into those prime factors in a way. Meaning our 3a minus 2018, it really doesn't matter, problem is symmetric in a and b, so it really doesn't matter which one of those you are going to take. So 3a minus 2018 could be equal to, for example, 1, because 1 times all of this bunch that we are going to have here is still going to give us 2018 squared. So it could be equal to 1. But it could also be equal to -1, so for example, because we want a and b to be element of the positive or negative integers, both. This is something that is going to hold here, because we could make it equal to -2018 squared. Okay, all of this, and it would still be in the set of solutions in some way. Okay, so this is the first one, but what could it be equal to 2? For example, 3a minus 2018 could be equal to 2, for example. Then this factor would be equal to 2 times 1009 squared. So it could be positive or -2, for example. And now you're going to go through all the combinations here, and this outtake you can find on my other channel. Welcome back. Now that we have computed each and every combination here, let us go ahead and solve those equations. Actually, I'm going to show you the first one, and then you can watch the rest of the outtake over on Flammy 2. So at first, 3a minus 2018 is equal to plus or minus 1. What you can notice here is that we can always add 2018 on each and every side here. Meaning 3a is always of the form 2018. And it does help for those factors, for example, to decompose 2018 into its prime factorization. And then plus or minus the factor that we are having, 1, for example. Now this is really easy to compute. Either we have 2019 as a solution, or we are going to have 2017 as a solution. And now you might notice something. In order for us to solve for a, we need to divide both sides by 3. Meaning either of those solutions, or both solutions, if they are both solutions, they must be divisible by 3. And it's really easy to actually see if they are divisible by 3. So 2019, we can make use of the digit sum test. So 2 plus 1 is 3, plus 9 is 12, that's divisible by 3. Meaning this thing is actually divisible by 3. And 2017, no, it's not, because if you subtract 3 from 2019, we get 2016. Doesn't work out. So 2019 is a possible solution here, meaning if we were to divide by 3, then a is equal to, okay, 700 would be, 700 times 3 would be 2100. So subtracting 91 divisible by 3 is 27, leaves us with 673. Okay, as being one of the first solutions, and the counterpart to the solution, 673, corresponds to plus or minus 1. The counterpart to this thing is actually positive 2 squared times 2009 squared, being expressed by this factor here. So we need to compute this. And now over to Flammy 2 and then watch the rest of the video. Alright, now that we are done with this piece of shit right here, there was a lot of work, we can go ahead and actually compute our a's. Meaning each and every solution that is underlined here, we need to divide by 3 in order for us to get our a. One thing I already said on Flammy 2 is that we get 8 solutions overall, but since a and b are symmetric, we only get 4. Meaning since they are symmetric in each other, we only get half as many solutions. Okay, does make perfect sense if you think about it. So the first one was obviously a being equal to 673, and now we are going to go ahead and divide 2 times 1008 by 3. So the next 8 that we are going to get is thus. Okay, 2 is not divisible by 3, so 1008, this is 900 plus 108. 108 is 90 plus 18, so this makes 6, and then 30, and then 300, so 336 times 2 is going to give us 672. So the next a that we are going to get is this thing divided by 3. This is 1 unit more, so one factor of 3 more, you could say, one summand of 3 more than 1008. So meaning instead of 336 we get 337, meaning overall that's 674 then. Alright. Next one is this divided by 3. Well, that's easy. 1009, that was not too hard. A being equal to 1009. And now the next one is going to be, okay, 1011. Yet again, we already computed this. This was 337 times 1009. I'm not going to elaborate on this any further. It's just some number, it really doesn't matter. 337. So next up, the next a is going to be, okay, here we had no solutions at all. Now what about this one? It's nicely divisible by 3, we have factor of 3. So 2 times 1009 is going to give us 2018. overall. That was easy to compute. And now next up, a being equal to, that's our only negative solution that we actually have. So 1008 is the thing divisible by 3, meaning we are going to get something negative at first. 2 times 1009 is 2018 times, and then 1008 divided by 3 was 336. Like I said, not going to elaborate on this any further. And now the last solution, 2019 is divisible by 3, and this was exactly 673. So this is 2018 times 673. And now we can find our 4 pairs, because now we can actually start to pair those together. So the first pair that we are going to get, AB, is the one with the factor 1 and the one with the factor 2 squared times 1009 squared. Okay, this is the counterpart, because 1 times 2018 squared is 2018 squared. Does make perfect sense. So this is overall 673, comma, and what was the thing corresponding to 2 squared times 1009 squared? It's exactly this last one that we are having here. So 2018 times 673. Okay, I hope you can see what we are doing here. So the next pair, you would in normal case write it out, but I'm too lazy for that right now, is, okay, we are done with this and we are done with this. Now what about 672? This was the one corresponding to 2 squared. No, it was the one corresponding to 2 in our case. So what is missing is this one, 2 times 1009 squared, this one. So overall, 2 times 1009 squared is this one. So negative 2018 times 336. Okay, next pair. So we are done with this and we are done with this. Now we have 674. This was the one corresponding to 2 squared. So 674, comma, and this is corresponding to, now we have 2 squared, so we need 1009 squared as the other factor. So meaning this is this one. 1009 times 337. Okay, and the last one is thus 1009 and 2018. That was easy, those were the last one. Let me check. Once again, 1009. Okay, this is the one with the 1009, and 2018 is corresponding to this one. Exactly, yes. And those are all the ordered pairs that you could possibly have. Yeah, that was quite a roundabout video with a lot of outtakes, but I hope you did enjoy it anyway. But before we actually end the video, I would like to thank today's sponsor Brilliant for sponsoring this video. And I for once would like to give you my honest opinion about Brilliant, because in normal case you only see me talking about it in the background most of the time, and I really would like to tell you a few things about Brilliant, because I really enjoy this website and I love doing live streams with you guys, and I love to just hear feedback from you, how you really enjoy Brilliant when working with it, learning for your STEM career using Brilliant and all this stuff. So Brilliant overall is an online learning platform with a lot of interactive exercises. So you can go over there and you want to find out something about Diophantine equations, elementary number theory, or for example, let's say competitive mathematics, what we did here today. All of this can be found over on Brilliant. And their course concept is really simple. You start off with introductory topics and work your way up to harder and harder exercises. And the exercises are pretty interactive. So you can play around with graphics and you can turn stuff on and off. And if you get an exercise there, you have to put in your answer and then you can check if it's actually right. And if it's not right, then you can check with the given answer provided by Brilliant. And it's pretty good. All the explanations in there are pretty well thought out and basically everything's really understandable. And they are expanding their repertoire of courses each and every month. So last month they, for example, released their mathematics history course, which is a really good course. So a lot of exercises in there combined with the interactive learning experience. It's a pretty good thing that you can experience there. And I really love Brilliant. I like going over there and just solving through a bunch of stuff. I for myself learned some new stuff over there. For example, Markov chains. So they have higher mathematics in there too. Or for example, bidual spaces, for example. A lot of stuff over there, and it's just absolutely brilliant, just like the name would suggest. So if you want to try it out, then make sure to use the link at the top of the description. With it, you are going to get 20% of an annual premium subscription and also free access to a big portion of print already. So you can try it out, see if it's something for you, and if it is, then get yourself the premium subscription because it's really worth it. They're expanding their repertoire each and every month, and so much new content is coming out each and every time. It's absolutely fabulous. So go over there and support the channel this way. If you did enjoy this video, please like and subscribe, make a comment, channel feedback. If you want to support the channel a bit more, buy those t-shirts I create, or support the channel on Patreon. Also go over to Flammable Maths too and subscribe there. And until the next video, I wish you guys a Flammable day. Ciao.